very likely to be cited. It's very likely to be read by our peers in the scientific community. So in a nutshell, this is why you should be concerned about regression analysis. So if you're a scientist and you want to increase your productivity, well, you have to learn how to do regression analysis. And so this bootcamp is designed to give you the skills to be able to do it and interpret it very well. So the whole of our lecture today is going to be framed around the concept of we either move forward or we move backward. And this is not a mystery, right? Like in most cases in life, or most scenarios in life, we sometimes have to take a step forward or we have to take steps backward. And if we understand this concept, that means we understand what regression analysis is. So in the next few screens, I'm going to show you some scenarios. And we're going to do a pop quiz where you will have to tell me whether what we need to do at that point is to move forward or to move backward. So let's start. So here, your assignment is to count the number of flower petals on the ground. Do you move forward or do you move backward? What are your thoughts? Let me see. Can I even see what people are typing? No, I can't. Lungla, any comments in the chat? You have to be my eyes now. There are flower petals on the ground. You have to count them. Do you move forward or do you move backward?
Forward,
okay.
Backward, forward.
Okay, who
move
said
forward?
We need one person who said forward. Like why do you move forward? Or the person who said backward, why move backward?
And you said why? Okay, let me.
Good evening.
Hello.
Am I audible?
Yes, you are.
Yes, you are.
Okay, so I think the answer is backward because you're trying to make a comment. You are trying to draw a conclusion from what is already there, what has already been, should I say, piled up for you to come and now observe.
Okay.
Thank you.
I don't want you to overthink this. Don't overcomplicate it. It's I promise you there are no tricks. It's just you want to count. Okay, let me move to the next example. All right, you want to count the number of fruits and vegetables in the basket. Do you move forward or do you move backward? So again, I promise you there are no trick questions here. It's just practical common sense. Do you move forward or do you move all the way back if you want to count the number of fruits in the basket?
So looking at this, Prof, I think that I have to move forward. Per the first one that you showed, I'm supposed to move backward. But looking at this one, I'll start from the bigger one. Then I'll move forward towards, I don't know whether it is orange or the last one. So I'll move forward. Okay, very good. You move forward. And the reason why you move forward is because you need to count the number of individual items. I mean, think of it, yes, right? Please. If you're a mile away, how are you supposed to count these items? If you are standing a mile away, you can't see them, right? Because your interest now is in the individual items in the basket. All right, let's move to the next one. Yes. Now you're on the ground, right? But your interest is to view the entire earth, not just the ground on which you stand. Do you move forward or do you move all the way backwards?
Not just the ground.
Sorry?
Jonathan?
I would probably move forward, but only because, again, I'm an English speaker, so I read left to right. So okay. I would probably go from the bottom left corner upwards.
But you're standing on the ground already. You want to see the picture of the whole globe, right? Not just the ground on which you're standing. So do you move away from the earth or towards the earth? You're standing on the ground already. But you want to see the whole earth, not just the ground on which you're standing.
Towards the earth, final approach.
Okay. I beg to differ, but let's move on. Let's take the next example. You want to view the entire forest, not just the tree by which you're standing. Do you move away from that tree or towards the tree? Again, your interest is to see the whole forest, not just the tree. Do you move away or do you move towards it?
I'll move away. My name is Esther from
Esther, yeah,
Nigeria. I'll move away because it will give me a better view of what I want to get.
absolutely, right? Now, I'm sure you've heard of the analogy of the elephant, right? Where different folks were asked, okay, they were all blindfolded, and then they said, okay, what do you think this is? They said, it's a fan, it's a spear, it's a snake. Now, who is correct and who is wrong? And if they're wrong, why is there so much? What is the reason for the systematic error here?
I think it's because they are viewing it from their own perspective. Different people viewing it from their own different areas. So they see what they see, looking at it from where they stand.
Very good. From where they stand. And that's because they are standing
Yeah.
to what?
Too close to the object.
Excellent. So that means that for you to see the whole object in its entirety, what must you do?
You move backwards.
Yeah, you have to move backwards, right? And that is what regression is. The literal meaning of the word regression means to step backwards, right? The etymology of regression means, from Latin, means the act of passing backwards, the act of returning backwards, right? And so you might be wondering, why would we want to go backwards? Well, it's because we're not necessarily interested in the fruit in the basket. We're interested in the bigger picture. We're not interested in seeing the trunk of the elephant or the legs of the elephant or the tail. We want to see the entire elephant in its entirety, right? So we must move backwards. Otherwise, we won't see the big picture. So regression analysis is all about moving backwards so that we don't see just the individual parts, but we focus on the bigger picture. So we can see the entire picture. That is what regression analysis is, right? So again, these are the answers to the pub quiz. Well, you've heard of the expression, someone can't see the forest for the trees. That means you are looking too intently at the individual data points that you fail to see the big picture. So if you want to see the whole forest, well, you got to move far away from the forest, right? Maybe go take a helicopter and move like hundreds of feet above the air. Now you can see the whole forest. That's the only way you can see the whole forest, by ignoring the individual points. So you have to give something to get something. By moving away from the forest, you no longer see the individual trees, but now you can see the whole forest. The same thing with the earth. Like the question of, okay, you're standing on the earth, but you want to see the whole earth. Well, how do you see that? Well, you have to go into space, all the way into space. All right, then you can now see the whole earth. And of course, when you're into space, you won't see your house. You can't say, oh, that's my house on 56, Ethiopian road, right? You won't see that level of detail anymore. So you lose the nuance, but you gain a bigger picture, right? So that is how you can see the whole earth, by moving away. So that, in a sense, is what regression analysis is. It's all about stepping backwards away from the data so that we don't necessarily care about the individual data points. We don't care about Barbara's data or Ilias' data point or Esther's data point as individuals. We want to see how the whole population fits, how the whole, the model behind the whole data, right? The bigger picture, not necessarily the individual data points. So this is, in a nutshell, what regression is. We are staring intently at this bigger picture, trying to understand, to make sense of what everything is. So in regression analysis, as the picture implies, you have two things in regression here. If we were the folks here staring into the telescope, and this was the moon, then there are always two things in the regression analysis. The thing that we are studying, the thing being studied, in this case, the moon. But in our study, that could be the outcome. It could be smoking, it could be tuberculosis, it could be anything. So you have that. And then secondly, you have the thing doing the studying, right? So there are always those two components to every regression analysis. The thing that is being studied, which we call the outcome, and the thing doing the studying, which we call the predictor. All right. Depending on the field or on the context, those two things have very different names too. We also call the outcome what's another name for the outcome variable? You can type it in the chat, or you can. What else do we call? What other names, popular names by which we call the outcome variable? Okay, Is it the dependent variable or is it an independent variable? Let's put it that way now. Is it dependent or independent?
So we have dependent.
Dependence.
Was
Let's say
that
dependent.
all right? Now, in other contexts, especially in social sciences, sometimes are referred to as the left-hand side variable or the right-hand side variable. Is the outcome the left-hand side variable or the right-hand side variable? What do you think?
Right. Left hand, right.
Okay. It is not, it is a left hand, because think of it as an equation. Say we are saying y equals to, x plus y, plus z. The y is the outcome, so it's on the left-hand side. You say y equals, so since it's the one that we're interested in, it is a left-hand side variable. All right. So this they say a picture is worth 1,000 words. So if we were to describe regression, this is it. This is a perfect picture for what regression is. We are standing far away from a moon. We are looking into the moon to see a picture of the shape of the moon in its entirety. We might not see the individual pieces of rocks on the moon, but we get a big picture, right? We have the thing being studied, which is the outcome, and we have a thing doing the studying, which is the predictor. Now, in terms of the approach to how we do regression analysis, there are also two ways in general. So imagine this young chap here says, okay, I'm just going to swing my telescope to the Milky Way galaxy and see whatever it is I can find in this starry night, right? He's more on a fishing expedition. He doesn't really know what he wants to do per se. He's just exploring. And so we call that kind of analysis exploratory analysis. So you might see things like we did an exploratory regression analysis to explore factors associated with X, Y, Z, all right? So that gives some context as to why we call it exploratory, because we don't have anything in mind a priori. We're just going with a blank mind and saying, well, let's just see what we find. Now, the opposite of an exploratory analysis will be more of confirmatory. So in this case, this young man says, let me point my telescope at a specific star to test my hypothesis about its brightness. So he has a specific agenda in mind. He's not just coming with a blank mind and saying, oh, let me just see what I can find. No. He's coming with a very specific agenda in mind, and that's why it's confirmatory. So it's either the hypothesis will be proved or disproved. So any regression analysis you run, regardless of whether it's logistic or linear or whatever, could be exploratory or it could be confirmatory in that context. So here is a pop quiz for you. 5 research questions here. So your job is to tell me whether it is exploratory or whether it's confirmatory. The first one is, the research question is, what factors most influence customer satisfaction in online retail environments? Is that an E for exploratory, or is that a C for confirmatory? So is that E or C?
E.
All right, great. Does increasing dosage for, things always gets in my way. Does increasing dosage of drug A reduce anxiety symptoms more effectively than the standard dose?
C. Confirmatory.
E.
Well, it's not E, right? We have a very specific thing in mind. We're looking at drug A versus dosage A versus dosage B for this drug A, right? We are comparing 2 doses to see how that affects the outcome, which is anxiety symptoms. So because we have we're not coming with a blank mind and saying, oh, let us just see what factors are associated with anxiety symptoms. No, we came with something very specific in mind, which was, how does dose A, the first dose and the second dose, compare in terms of this outcome? So that is why it is not exploratory. All right, the third one, how do social media usage patterns vary across different age groups? Is that an E or a C?
E.
Okay, that is correct. It's an exploratory. What are the emerging trends in remote work preferences post-COVID-19? Is that an E or a C? Excellent. C? How is that a C? I would like some justification for those of you who said C. Why do you conclude it's a C? Okay, well. Okay, go ahead, please. Yes.
Because I'm not seeing any explanatory variable there.
So the question
That
is, what
is
are the emerging
specific.
trends, right? What are the, it's very open-ended question. What are the emerging trends? Like trends in what exactly are you talking about?
Yes.
Trends
So,
in X? Is it trends in coming to telework? Is it terms in, it could be anything under the sun, right? We don't even know.
yes.
So plus it's just open-ended, it's exploratory.
Okay.
Do you
I also
yes, go ahead.
I also think that when the sentence begins with what, I'm also getting the clue there. Then when it begins with what, it means that you are not being specific.
Well, that may
But
not
when,
work.
when it begins with das, it means that you are focusing on something das, so it means that it's narrowing.
Well, that I like your effort, but that may not work in all cases, right? I could say, what is the association between, use of e-cigarettes and smoking cessation? I'm trying to measure the association between very specific exposure and a very specific outcome. It's confirmatory. So, so don't just rely on whether the word starts with what. Try and understand it at least philosophically, and I think that would be a better way to go. We good?
Yes.
All right.
Yeah.
Last question. Is that an E or a C?
C.
Excellent. All right. So what do we get from regression analysis? They give us models to explain reality, right? So that's why you hear people talk about a regression model or a logistic regression model, because that is what we are getting from a regression analysis. It gives us a model. So my question, this is an pop quiz. What do you see on the screen?
Apple.
Wrong.
Apple.
Wrong. That's wrong.
Ripe apple, green leaf.
That is wrong.
Red apple.
That is wrong.
A red apple and a leaf.
That is very wrong.
Fruit.
A picture of an apple.
Sorry?
A picture of an apple.
Excellent. Or let's be more scientific. I want you to frame that your answer in a more scientific way. What do you see?
The model of an apple.
Image.
Excellent.
An image of an apple.
No, let's not go with image. Let's stick with model, okay? It's a model. Now, why is it a model?
An image of
Why were the other answers wrong? Why were the other answers wrong?
Because it's not reality. You are just actually looking at it from afar. So
Because
it's not reality. It's not something that you can touch.
You cannot eat this apple, right? You cannot hold it in your hand. You can't smell it. So if we cannot eat it, if we cannot taste it, if we cannot hold it in our hands, then of what use is it then? Why do we need a model if we cannot eat it, if we cannot hold it, if we cannot do all of those things we mentioned? Why in the world do we then need a model of an apple? Who can think of a reason why then we might need it?
To help us understand what an apple is.
Explain probably how a real apple looks like.
To give us an idea of how the reality is.
Excellent. Imagine somebody, there's some parts of the world where they don't have apples, right? Like there are many parts of the world where they may never have seen an apple, right?
Yes.
So how then do you communicate to this individual what an apple is? See, that's when
model. By giving them a model.
So we use models. So we use models when there is no data, right? When we don't have actual real world data, then we use model. If we have an apple, we don't need a model. All right. If we have an actual apple, then there's no need to draw a picture of an apple. All right. Yeah. So when we have data, we don't need models. We need models because we need to simulate some aspect of reality that we don't have data for. Right. And that's how you need to understand regression analysis in that context, that they're giving us a simplified version of reality. This is simplified because this is 2D. A real apple is in 3D. We cannot eat this, whereas a real apple, we can eat that. So in relation to the real apple, this is a very hyper simplified model, but it's useful too, because it still helps us to explain the world to somebody who might not otherwise see an apple. So that when that guy finally sees an apple, it's like, oh, I see. I think I know what this is. This is an apple because I have seen a model of an apple. So that's why we fit regression models, so that we have a simplified version of reality, so that we can explain the world to people, so they can understand too. Now, you must also understand that all models are wrong, but some are useful. So don't be so confident in your regression model, right? It is wrong. Or like, Judge Box famously said, it might have some use, but all models are wrong. So you have to understand that going in, that, it serves some purpose, but of course, that's why we try to measure uncertainty with our regression analysis. Now, for us to understand regression, we need to understand certain things, because from next week, we'll be talking about a lot of things. So we all need to be on the same page about some concepts that are actually basic, but sometimes are misunderstood. So the first on that list is hypothesis testing and p-values. Everybody talks about p-values, but nobody knows what p-values are. So we need to clarify. We cannot I can't just assume you all know it. So I just have to go over it. So if you're an expert in p-values and you're feeling bored, just hang in there. We'll get over it fast. We also have to talk about some terms that are, again, pretty used, but misused as well. Univariate, bivariate, multivariate, and multivariable. What do these things mean and how do we use them? We need to understand bias and validity. We need to talk about types 1 and 2 error. And we need to talk about power and sample size requirements, because obviously regression analysis is part of inferential statistics. That means that we want to make inferences. And for us to make those inferences, that assumes that we have enough power to make those inferences. Imagine a research being like a spacecraft going to the moon, and the sample size is like the fuel in that rocket ship. Obviously, if you don't have enough fuel, you can't get to the moon, right? So if you don't have enough power to fuel your hypothesis, you won't get the results you desire, and you might end up coming with the wrong conclusion and misleading all of us. So we need to talk about sample size requirements, because you cannot talk about regression without talking about all of these things. So why I know you guys would love to jump into logistic regression, and we need to build on the foundation first. And so that's the purpose of this first lecture, so that we're all on the same page on this basic foundational concepts. All right, let's talk about the first set of things we want to talk about, which is truth. Now, every single thing you see in the world can be explained by one of 3 phenomena. It's either the truth, it's either chance, or it's bias. So everything you see in the world, whether it's something in media or whether it's any observation, can be explained by one of those 3 things. It's either it's truth, or it's chance, or it's bias. Truth is what we desire. We want to find validity. Another name for truth is validity, right? And that's when you do a research, what you are actually doing is you're trying to find the truth, right? That's a very simple way to explore it. So when you say, what is the relationship between smoking and lung cancer? Another way to say that simply is, what is really the truth between this smoking and lung cancer? Like, what is the truth about it, right? So any research you do, you are trying to identify the truth. But the challenge is that truth is not just hanging in space where you just go and pluck it like a mango tree. Truth is buried and intertwined with chance and bias. So for you to find out the truth, you have to dig and extricate it from bias and from chance, right? And that's where regression comes in. But you need to understand these 3 things, right? That, okay, there's truth, but then there's chance and there's bias. And the whole point of regression is to separate the truth from bias and from chance. Now, bias, we'll talk about bias quite a bit in this class, because that is the whole reason why we do regression. Bias means systematic error, right? And bias is different from error, because bias tends to be systematic, whereas error is at random. So it's like bias, you can think of bias like, or error like an honest mistake, whereas bias means, it's not an honest mistake. It's a pattern to it. You are just being deliberately deceptive. That's what bias, you can think of it that way. So error means it's at random, whereas bias means it's systematic. Now, in epidemiology, there are 3 main types of bias we worry about: confounding bias, selection bias, and measurement bias. We'll talk about these things in the next few slides, but you need to understand these things at a very, very basic level to be able to do regression and interpret them well. And then, so truth, again, is what we are trying to find. Bias is systematic error. Chance is now random error. And that's why we use p-values. So why we use p-values to account for for chance, to control for chance. So again, we'll talk about these principles extensively in the next few slides. So when you're doing your research, you really want to ask yourself, so what truth am I offering in my study? Is it the whole truth, or is it the whole truth? The truth with holes, right? So, and this is the problem with, this is why journals would not necessarily be so enthusiastic publishing your paper that just has descriptive analysis, because it is the whole truth, the truth with holes, right? Because there are so many alternative explanations. If you said, for example, that smokers are more likely to, smoking, for example, is associated with hyperkeratosis, right? So you might end up saying, oh, smokers have healthier mouths. It's like, okay, is that the whole truth, or is that the truth with holes? What are alternative explanations? So the problem with descriptive analysis that don't have regression in it is that you just report the superficial truth. You don't really dig deep to see, are there alternative explanations, right? Have we adjusted for so and so? And by the way, we'll explain what adjusting means in a minute, right? So, but the bottom line is that I want you to know that your study could either be the first one, which is the whole truth and nothing else but the truth, or it could be a truth with holes, right? Which is no truth at all. And so that is why, again, we do regression analysis. Now, let's talk about some terms that we use a lot in regression or analysis to make sure that we're all on the same page. So when you have one dependent variable and you analyze it, that's called a univariate analysis. And this is something that you find humorously, quite interestingly, mistaken even in top journals. Just this morning, I have to show you guys this. Just when I was looking at a paper in JAMA, and actually saw a paper. Let me show you this. I just have to show you this. And let's see, where was this paper? Let's look at it. So that you can see how even in the topmost journals, sometimes some of these things slip through the cracks, and why we don't want your paper to be, if I can find this, let's see. Home. What was this paper? It was quite hilarious. So I'm like, okay, these authors need to have a basic instruction about difference between bivariate, univariate. If I cannot find it now, I will definitely look for it afterwards and share with you. Let me see if it's this one. But the authors essentially completely mixed up the meanings of the word univariate and bivariate, and let's see if it's this one. If it's not, I will definitely look for it and share with you guys after the class, just to save time. Let's see. So I found it. So this table 2 says participant characteristics by comment tone. Just forget about the context, but just what we want to focus on is on this table. So here, what they're doing is they look at this characteristic, and they're comparing across the 3 groups. There's a group neutral, group negative, group neutral, and group positive. And then they have a p-value for those comparisons. And interestingly enough, they call this univariate analysis. Now, in this paper, there are a lot of other things that are just not right, in terms of the statistical approach. Now, what we just saw there is not univariate. That is bivariate. Univariate is when you are just looking at one single, as the name implies, one single variable. That is, for example, if I look at overall means or overall prevalence or medians in the overall population, that is univariate. I'm just looking at one variable. It is impossible to have a univariate analysis and have p-values, because p-value means you're comparing two things. So once p-values enter into the picture, it's not univariate. It's now at least bivariate or multivariable. So univariate, please, so don't make that mistake. Univariate means, like uni means one. Bivariate means bi means two. So in this case, you are stratifying, for example, prevalence. Like that example we saw, where they were looking at, for example, mean of age across those three groups of that other variable. So that is bivariate. So stratified prevalence or stratified means or unadjusted regression analysis. All of those are bivariate analysis. In that case, you have one dependent variable and one independent variable. In univariate, you have one dependent variable and no independent variable. Now, let's go on. Multivariable is when you have one dependent variable and two or more independent variables. So one outcome and two or more predictors. That is multivariable. Now, this is where a lot of researchers get it wrong. Researchers love to use this word multivariate. And 95% of the times they're using it wrong. So they might want to say, what they actually mean to say is multivariable logistic regression, but they end up saying multivariate logistic regression. So let's explain what those terms mean and the differences between them. Multivariate could mean one of two things. It could mean you have two or more outcomes. Take note, multivariable, you only have one outcome variable. In multivariate, you might have two or more outcome variables and you have one or more independent variables. For example, in multivariate ANOVA is an example of a multivariate analysis. It could also mean that you have two or more outcome variables and you have no predictor variable. That means that all the variables in analysis are on equal footing. There is no one that is an outcome and then the other ones being predictors. They are all outcomes. So think of things like factor analysis or principal component analysis, right? In those cases, you don't have a predictor per se. They are all outcomes and you could have 10 or 15 of them, but definitely more than two or more. So bottom line is that when you have one outcome and multiple predictors, it is not multivariate, it is multivariable. So let's please use the proper language when we're writing in our papers. All right, let's use an analogy to again explain univariate, bivariate, and multivariable. You can think of boiling an egg as univariate. There is just the egg, right? There's nothing added to the egg, it's just plain hard-boiled egg. That is univariate. Now, if we take that egg and then we add pepper to it, now it's not just the egg, we have the pepper plus the egg, that is bivariate. So when we're eating the egg, we're eating a bivariated egg, right? If such a term exists. So, because the egg plus some seasoning, which is in this case, black pepper. Now, what if we now decided to go to town? We now added a whole bunch of stuff. We have toast and we have guacamole and all manner of stuff. Now that is multivariable because there are a whole bunch of stuff in that dish now beyond just the egg. We've added a whole bunch of things. And why are we adding a lot of things? To make it nice and interesting and nutritious. So that's one way you can also conceptualize the difference between univariate, bivariate, and multivariable. All right, here's quiz time. This is now your time to show that you understand this concept. I'm going to show you a screen, and you're going to tell me what you see on that analysis, on that screen, whether it's univariate, bivariate, multivariable, or multivariate. So here, this is showing menthol product prices across different products. So you have prices for cigarettes, for cigars, smokeless tobacco, and roll your own tobacco. Is this, what kind of analysis is this?
For me, univariate.
Is univariate.
Okay.
Univariate.
Excellent. It is univariate. Why is it not bivariate? Why is okay? Let me ask you
It's just one product.
Okay. Why is it not? Why somebody might say we have 1, 2, 3, 4 products, and so is that multivariable? Why would that be wrong?
Me, I was thinking it's bivariate.
It's not.
Why do you say bivariate?
Because like I'm seeing here the price and something also around. So I was thinking it's bivariate.
Okay. Okay. So, but it's just the price for each. Imagine each of these items as a row in your data set, right? Each of its tobacco product is a row in your data set, and then the prices are the column. How many columns do you have?
4. I have 4 columns.
Are you sure? Each of the tobacco products is a row, and their price is in a column, right? The price is a variable. How many columns?
2 columns.
Sorry?
2 columns. Just 2 columns.
1 column. 1.
2 columns.
1 for cigarette, 1 for price.
No, you're not hearing me. Let me explain myself again. Each tobacco product is a row. I think what is confusing you here is that we're looking at tobacco products. But imagine this way, these are like the units of observation. So we have each tobacco product is a row in your Excel spreadsheet. It's a row of its own. And then the price is it's a variable of its own. How many variables do you have in that data set?
1 variable. You have only 1 variable.
Okay, all right. Let's do this then. Okay, let's just do this.
You have only 1 variable, which is the price of the cigarette.
All right, don't worry, we're going to do it.
So in that case, you can only find the mean standard deviation.
Okay, we have cigarettes, right? We have cigars. We have smokeless tobacco. And we have roll your own tobacco. Those are the different products we are assessing in our study. And here you have price. So the price for cigarettes is, I'm just making this up, 12.25. The one for cigars is 10.21. The one for smokeless tobacco is 3.44. The one for RYO is 5.44. So, ladies and gentlemen, how many variables do we have?
2. 1 variable.
1 variable. Just 1
How
variable.
come some people are still saying 2?
We have 1 variable, which is the price of the cigarette.
So,
We have 3.
I am baffled how some people are still saying it's 2 variables. This is okay. Variables refers to columns.
Hello.
Variables are columns.
How do you account for the items list?
It's 2 variable.
How do you account for items? The items are the unit of observation. The unit of observation.
We have 4 variables.
We have 4. We have 4.
We have 4 variables, which are the things you listed: the cigarettes, the cigar, the tobacco, and the oil.
Okay, let me explain. I think there's a problem with understanding what a variable is. A variable is a column. The columns are what we call the variables. Okay? The rows are the units of observation. The rows could be people. In this case, they are tobacco products, but it could well be Johnny and Jack and John Doe, right? And Jane Doe, right? Typically, we're used to the rows being individuals, but the rows could be anything. It could be tobacco products, it could be anything. In this case, our unit of observation are tobacco products, which are the rows. So rows, a data set is made up of rows and columns. So in this case, the outcome here is price, which is 1 column. So that is why this is called univariate, because there's only 1 variable we're analyzing for a different product. I hope that is clear.
Sure.
All right.
Yes. Yeah. And when you relate it to even mattress dimension, so it's still the same 1 dimension.
All right.
So in mattress, this is also 1-dimensional table that you are supposed to have.
All right, moving on. Is this looking at trends in menthol cigarette smoking over time? Is this univariate, bivariate, multivariable, or multivariate?
Univariate.
Okay.
Univariate.
So
Univariate for me.
Okay. What do you have on the what do you have on the x-axis?
It's bivariant because
Y-axis.
there's an aspect of time.
That's the y-axis.
What do you have on the y-axis?
Prevalence.
Prevalence of what?
Yes. Of smoking among
It's
Very good.
prevalence represents the percentage of
Okay.
the number of times it's on call.
All right, and this row, the x-axis represents what?
The
years.
Or time, right?
About time.
So how many variables are we looking at now?
Two.
So if we're looking at two variables, what kind of analysis is that?
Bivariate.
So this is the bivariate analysis. All right. So here we're looking at how the percentage of e-cigarettes and tobacco products differ by e-cigarette and any flavored non-cigarette tobacco product used by mental status. All right. We're comparing mental users and non-mental users in the use of e-cigarettes. So the green represents the mental smokers, mental cigarette smokers, and the red represents non-mental cigarette smokers. And this is indicating ever use of e-cigarettes, current use of e-cigarettes, and current use of any flavored non-cigarette tobacco products. What kind of analysis is this? Sorry?
Multivariable.
Multivariate.
Okay.
Bivariate.
This is a trick question. This is a trick question, and the reason why I put this to trick you is that when people see a lot of results on the page, they just say, "Oh, it's multivariable." But seeing many results, seeing a lot of results on the page does not mean it's multivariable. You have to look at each unit of analysis, each individual result. Is it multivariable?
It's bivariate.
Exactly. So this is why this
I
is
think it's bivariate.
And
because it
What about this
basically
one?
describes. Okay.
This is looking at support for bans on characterizing flavors among all adults in the US. So we have the results. The variable is support for bans. It's presented overall and broken down by gender, by age, and every other thing. Is it univariate, bivariate, multivariable, or multivariate?
Bivariate.
Excellent. Again, this was to trick you by displaying a whole lot of things on the screen and hoping you guys would be confused, but you guys weren't. Alrighty. Now, what of this? This is showing odds of mental use among current smokers in grades 6 to 12. And this is looking at all these variables. What kind of analysis is this?
Multivariate.
Bivariate. And then multivariate.
Okay.
Bivariate.
I can hear the multi, but I can't hear what ends.
Bivariate.
Multivariable and
Multivariable.
Multivariate.
Why is it multivariable and not multivariate?
Multivariable.
It is multivariable because the predictor variables are many, but the outcome variable is just one.
Excellent. As far as you have only one outcome, that means that's multivariable, right? Once you have two or more outcomes, that's multivariate. So please, the distinction is quite clear. So please don't mix up those terms together. So what does it mean to adjust? I'm sure if you read any scientific literature, you've heard of that term. Oh, we adjusted for X, Y, and Z. We controlled for X, Y, and Z. What does it mean? Well, this is the best picture I can think of in terms of explaining what adjust means. So, who can describe to us what do you see in this picture? And that's not a trick question, truly. Like, what do you see in the picture?
It's a boarded passengers on plane.
Okay.
That is zoomed.
No, it's
Model of
plane hostess 7 refreshments on the flight.
Okay, so how many people are moving at the time?
One person.
That's one.
Person. So one person is moving at the time, and every other person is what?
Sitting.
Seated.
They are all seated,
and they are strapped in their seats. Why are we strapping them in their seats? So that they don't move, right? So that means, so this is what we mean by adjust, right? So that only one person, right, moves at a time. So we can see, oh wow, if the pilot says, let's see how does the airplane behave when people are moving, or when the behavior is when, for example, drinks are being served. Well, for us to observe that behavior, we need everybody to be in their seats. So we are adjusting for every person's movement by keeping them strapped. So in other words, we're trying to delete them from a picture completely and just zoom in on what we want. That is what we call adjusting for something. So adjusting means we want to keep them strapped down in their seats. We want to hold them, keep them out of the picture so that we just focus only on the outcome, right? So let's go back to that previous regression analysis here, right? In this analysis here, the table is looking at factors associated with menthol use among current smokers. So they took a whole bunch of cigarette smokers and then asked them, do you smoke menthol? Like the kind of cigarette you smoke, is it menthol or non-menthol? So we're trying to see what are the factors that are associated with menthol use. So here, let's explain this and let's now really understand the concept of adjusting or adjusting for factors. So here we say that females had, compared to males, females had 1.17 higher odds. Okay, this is not significant. Let's just focus on the results that were significant. So the reference group here is white. So we're saying compared to white, blacks had 3.19 higher odds of reporting menthol use, right? So the odds of smoking menthol cigarettes were 3.19 higher among blacks compared to white, but holding all other variables constant. So that means that when we're looking at blacks, the relationship between black and white, every other thing in this table is held constant. And what do we mean held constant? We mean that we are strapping them in their seats. It means that we're keeping them all to a constant value. So that means that when we're looking at race, everybody, we are assuming that they are male because male is a reference group. So everybody in that data set is male at that time. Everybody in that data set is in middle school at that time. So that there are no differences in sex, no differences in school level. Everybody is, the reference smokes at 1+ hour. Everybody has does not have a medical condition, right? So everybody is held constant at the level of a reference group. If it's a continuous variable, we hold them at their mean. Please mute yourself if you're not contributing to this particular discussion. So that's what we mean by holding things constant. Is again back to that picture of a plane. We are looking at the relationship between blacks and whites, and we want complete silence. We want every other variable to be silent so that we can just focus on that relationship between blacks and whites. So we hold everybody constant at a particular value. So, and that value is supplied by us, right? So that is why we use reference groups. So the whole point of reference group is that is the point at which we hold everybody constant. So again, when we look at the relationship between blacks and whites, everybody is a male at that time because we're not looking at males. We're not looking at gender at that time. So all the participants in our study are held with fixed gender so that the differences we observe can't be because of differences in gender because everybody is the same gender at that point, at least statistically. That is what we mean by adjusting or controlling for things. And that's what regression analysis does. It allows us to see the independent effect of something while we hold every other thing constant. And if you don't understand this now, don't worry, we'll have 4 weeks to really go into this. We're going to cover all of that extensively. So you'll be pretty sure by that time what that means. So we've talked about truth. Let's talk about truth and how it affects our results. Now, sorry, Lion King, you have your hand up. You have a question?
Yes, Prof. Going back to the table you presented, the investigator didn't actually bring the p-value. So is it accepted in a journal like this?
So the confidence
you already have confidence intervals. So you don't have to show confidence intervals and p-value. Confidence intervals suffice.
Wow, this is my first time of hearing this. So
okay, great. All right, so let's talk about those three elements, and then we'll then proceed with again providing context. So all of this is to provide you context so that when we start talking about, when we start fitting regression models and analyzing them, you won't be like lost. So if you've been to our previous classes, you should be well familiar with what we call the cycle of inference. We take a sample from the population, and from that sample, we make inferences. That is the cycle of inference. External validity has to do with how well can we take results from that sample and generalize them back to that population. That is what we mean by external validity. Internal validity has to do with to what extent is our study protected from bias, right? And remember, we'll talk about 3 types of bias: confounding bias, measurement bias, and selection bias. To what extent is our study protected from those biases? That is what we mean by internal validity. Now let's talk about bias, since we're talking about the relationship between bias and internal validity. So let's think of a study as people plus the answers. So when you take a bunch of people plus the answers that they gave us to whatever question we asked, that is what we mean by a study. So a study is equal to people plus the answers. Now, the 3 types of biases can be mapped to that framework we talked about. When there's a problem with the people, that's a selection bias. So remember, we said a study is equal to people plus the answers. Well, if there's a problem with how we selected the people, that is selection bias. If there's a problem with how we collected their answers, that is measurement bias. And confounding bias is a problem where we cannot know who said what. There's so much noise in the air that it's hard for us to know, was it this person that said this? It's hard for us to know for sure, right? So confounding bias creates a scenario whereby we have a whole bunch of alternative explanation. There's just so much noise in the air that we can't really say that, this relationship we are looking, is it truly coming from this exposure? Or is it just coming from background noise, right? So again, simply put, a study is people and answers. Problems with how we selected the people is selection bias. Problem with how we fetched or collected the answers is measurement bias. And background noise that distorts the truth is what we call confounding bias. So again, this is another way of visualizing selection bias. How did people enter the study and how did they exit? If there are differences between the study arms, then that gives us selection bias. You can think of confounding bias as the nosy neighbor, right? You know, it's always poking their head in wherever they're not wanted. Like, dude, you're not invited to the party. Why are you here? All right. So that's why we call confounding variables the nuisance variable in epidemiology, because they are unwanted, but they just want to be there by all means. So regression analysis is all about removing this guy, this nosy guy from our analysis. So if you were to summarize regression in one word, that is it. Yeah, we want to get rid of this guy so that we can get the big picture of the relationships without interference, without any noise, right? So, you know, that's a key objective of analysis, to control for confounding or to remove those nosy neighbors from our picture. Now, all right, this is a test of your understanding of a bias. Okay, let's see how well you understand this. A national household survey that uses landline phones systematically underrepresents youth and people in rural areas. What kind of bias is that?
Selection bias.
Selection bias.
Excellent. Many immigrants refuse to participate in the government study because of concerns about deportation.
Measurement.
Selection bias.
Selection bias.
Selection. Remember, we say the study is people and their answers. The problem with how people were selected, regardless of whether it involved how they came into the study or how they exited the study, gives you selection bias. So this is the selection bias issue. In a study examining gender differences in tobacco use, pregnant women who smoke are very likely to deny being smokers.
Measurement.
Measurement bias.
In a study of very aged and largely retired population, the study found that the risk of dying is much higher among young people.
Confounding.
Because there's noise, there's definitely some noise in that data that's preventing us. All right, now let's go back to the third pin, which is chance. So remember, we said every phenomenon in the universe can be explained by truth, chance, or bias. You got to understand those things for you to even do regression analysis. Otherwise, you might just be putting out garbage. So let's talk about chance. For us to understand chance, we need to understand the concept of decision-making and error rates, right? If we took all the people in the world and put them into categories, we can say there are 2 types of people: alpha males or alpha females, and beta males or beta females. So alpha males just rush in, right? Like they're fearless, they're very rash. So they just rush in any scenario. There's a burning house, they rush in. the building is collapsing, just rushing, right? So the problem here is that the risk is you might lose everything, right? You might get sure you can get accolades, but then there's a risk of you running into trouble with just that brash approach to things. Then the better approach is just a very timid approach that refuses to engage, right? And so, sorry. Can you guys mute yourself, please, if you're not interacting with the content, please? So alpha is very, very frontal and just rushing into everything. Beta is very reserved, very conservative. And by being beta, right, you end up losing up on opportunities because maybe there was an opportunity for you to shine and you just stay in the background and you just did not shine, right? So you end up losing on some things because you are not forward enough. So those are two risks. And that's how you want to consider statistics in general, like, because decision making in statistics, when we analyze data, we're actually making decisions. And all our decisions in data too fall into those two groups. It's either we're alpha and just rushing into making decisions and just making conclusions, or we are beta and we're just very timid and we refuse to make a conclusion because for whatever reason, we're afraid. Now, this is a Greek alphabet. And I just wanted to show you that alpha is the first letter in the Greek alphabet and beta is the second letter in the Greek alphabet. So issues of alpha are called type 1 error because it is the first letter in the Greek alphabet. And issues of beta are called type 2 errors because they are type 2 errors because beta is the second letter in the Greek alphabet. So now let's explain the concept of hypothesis testing because you cannot talk about regression without talking about hypothesis testing. So when we test hypotheses, we usually have a null hypothesis and an alternative hypothesis. The null hypothesis is that nothing interesting is happening here. That's why I see the guy yawning, right? It's like, geez, this is so boring. Nothing is happening here. The alternative hypothesis is that, oh, there's a party happening here. Something very interesting is happening here. So that's how you want to understand the null and the hypothesis. So when you read papers, you see that they will say statistical significance was set at p less than or p equals 0.05, or the alpha threshold was at the 5% level. What does that mean? Well, an alpha error rate tells us that it's you can simply understand it in the context of the number of 100 people you helped, how many did you actually harm? If a study concluded that this drug is associated with helping, let's say we compare two drugs, drug A and drug B, and we concluded that drug A is completely useless. It does not save anybody. And drug B saves 100 lives. Of those 100 people we saved, how many did we actually harm, right? Or in other words, what's the false positive rate associated with that study? So if we say that the p-value threshold was 0.01 or alpha of 1%, we are willing to accept that for every 100 people we helped, we actually harmed 1%, right? If the alpha rate is 5%, we are willing to accept that, well, we accept upfront that we are willing to trade that for every 100 people we helped, we actually harmed 5 of them, right? And by harm, I mean like false positive rate. So that is the concept of the alpha. Or if it's 10% alpha, you are willing to accept that for every 100 people you helped, you are willing to acknowledge that 10 of them were actually harmed or not helped at all, right? So that means that, now this is a quiz for you. In a very critical situation, do you want to have a large alpha or a very small alpha? If it's a life or death situation, right? Do you want a big alpha or a small alpha for your threshold? Yes, I see some hands up. You can unmute and speak.
Very small. Very small alpha.
Exactly. So if it's a life and death matter, obviously you want to have it as small and as possible, right? So that the risk of harming people is very low. So one of the take-home messages I really want you to get from this class today is that people somehow believe that this p-value of 0.05 was sent to us by God and delivered by angels. No, it is set contextually in your study, right? It's dependent on a lot of things. For your study, I can choose to have an alpha level of 0.1 or 0.01. You're not forced to use 0.05 as a threshold. And this is why you need to understand these fundamental concepts. Because if you don't understand, how then do you even begin to apply it in your research, right? So that is why we have to go over this concept so we're all on the same page as to what that means. So this is another way of thinking about p-value. You can think of it as a lie detector test. When you take a lie detector test, I have never taken one, but I've watched in movies. They ask you some opening questions first, right? Like, oh, is your name Israel Agaku? Is today Friday, August 9th? Are you sitting down? Are you wearing shoes right now? Are you aware? Sarah, please, can we kindly mute ourselves? We're not talking. Regine Kwa, can you kindly mute yourself? Jeez, you're giving me a headache. So these are standard questions we ask, right? And the whole reason is to establish the truth. That is the reason why you ask those baseline questions, to establish the truth. So that when they now ask you, so did you steal that money? And you now give an answer that is quite different. It's like, okay, the response under the test is quite different from the baseline we've established from the truth. Because for each question you are asked and you give an answer, the lie detector measures your biomarker levels, right, and how you respond. So that when something strays from that truth, it's like, oh, this is not consistent with the observation of the truth, right? So the null hypothesis is this part here, which is, oh, this is so boring. Nothing is happening here. But when you start lying, it's like, oh, something is happening here, because the responses we are seeing here are quite different compared to when nothing was happening. So bottom line of what we're saying is that the null hypothesis, the p-value is a conditional probability, right? We're always comparing the response to when nothing was happening, right? So that is how you want to understand a p-value. So the question is, what is the probability of us seeing this kind of very, very strange responses, right? If indeed nothing was happening. And if we now say that, oh, that probability is so small, we're like, you're lying. You stole that money, didn't you? Right? So that is how you want to think of p-values. We are always comparing whatever we see to the scenario when nothing was happening. So we've talked about bivariate, univariate, and multivariable. We're going to discuss much of this in the next few series, but I'll just touch about those various ones just a little. So univariate could mean, what is the mean value of X? What is the median of X? What is the count of X? Or what percentage of people reported X? All of those are univariate. Bivariate could be, what is the difference in the mean value of X between groups Y and Z, right? So now we're comparing two variables, and that makes it bivariate. Multivariable, what is the difference in the mean value of X between groups Y and Z after holding A, B, and C constant? Again, we're holding all the variables constant and trying to see the independent effect of that exposure group. So we're going to cover all of this. Now, the next 4 weeks, we're going to talk a lot about the different types of regression analysis, binary logistics. So we won't go faster than our shadow now. But again, this is just to give you a full glimpse of what we're going to be covering over the next few weeks. We'll go over each type of regression in detail. We will fit it in theta and R. We will learn how to interpret the results and how to do possible sensitivity analysis as well. All right. Very, very important things to take note of when doing regression analysis. You want to make sure that you consider issues of type 1 and type 2 error. So the biggest issue with type 2 error is small sample sizes. So we cannot talk about issues of regression or baseline knowledge about regression without talking about sample size and power. So here is a pop quiz for you. Let's see the relationship between effects, size, and power. So the pop quiz is, the more powerful a microscope is, the blank, the size of things it can detect. What is blank?
Smaller.
Okay.
Smaller.
Right, Greg.
Smaller.
Exactly. So you exactly. So so if we want to detect very small, got it. So if we want to detect very small differences, that means we need a very powerful study. You know, if we want the smaller differences we want to detect, that means that the more powerful our study must be, or the bigger the sample size our study will have to be. So that is something we have to keep in mind. Now, sample size has to be done precisely because there is such a thing as too much sample size. And, you know, I love referring back to this paper because it's quite alarming. This paper, the bottom line of the paper is that of 215 randomized trials published in some of the biggest journals, they found that only 34% correctly calculated sample size. Now, if that is not alarming, I don't know what is alarming then. And these were some of the biggest journals like the Lancet, New England Journal of Medicine, and so on and so forth. So bottom line is that you have to determine sample size correctly. And that you also have to know how to calculate sample size for when your analysis is exploratory versus when it's confirmatory. Because when we're doing exploratory analysis, the most important thing we're concerned about is precision. Precision essentially is how wide our confidence intervals, how narrow or how wide our confidence intervals. That's what precision is. But when we are calculating sample size for confirmatory analysis, we are worried about power. Power means the ability to detect differences where they exist. So sample size calculation is quite different for exploratory versus for confirmatory analysis. So we're going to use the rest of this time to see how we can set up our sample size calculation when we are doing sample size calculation for power for a confirmatory study as well as for an exploratory study, so that we can keep that in mind and avoid type 2 error. Type 2 error simply means that there's a difference in nature, but our study failed to detect that difference because our sample size was too small. All right, so now I'll go ahead and show you how to calculate the sample size for when we have a confirmatory study as well as just a descriptive analysis, and then I will then take questions. All right, let's go over here. So we're going to use the chi-squares platform to calculate our sample size for our, okay. So we're going to use the chi-squares platform to calculate sample size under the scenario of a confirmatory study as well as a more exploratory analysis. And we can now see the kind of things we emphasize the most when we are looking at a confirmatory study versus when we're looking at an exploratory one. For those of you who don't know what a chi-squares platform is, it's a one-stop shop for scientific research. The chi-squares platform allows you to design your study, like calculate sample size, to sample, to design surveys, to collect data, and so many other things. But we're not interested in those other elements today. For now, what we're interested in is how do we calculate sample size for a study so that we ensure that our results are adequately powered. So let me log in.
So how do you get into the chi-square platform? How do you have access to it?
Lungle will share the link with you. Lungle, can you kindly share a link to the platform with everyone, please?
I've shared it.
Okay, great, thanks. So so on the panel on the left, you see some of the functionalities of the platform. Survey design is where you design your survey. Sampling is where you draw a representative sample. Survey bank is a repository of thousands of questions. But what we're interested in now is sample size, which is how do we calculate sample size for our study? Now, let's start with a confirmatory study. A confirmatory study will be a comparative study with two arms. So remember, those examples we looked at earlier, we're looking at a specific exposure. How does, for example, we said, how does dose 1 compare with dose 2 in reducing symptoms of anxiety? So where the exposure is 2 arms, which is the first arm is dose 1, the second arm is dose 2. Our outcome is symptoms of anxiety. So in that case, we're looking at a comparative study. Comparative because we're comparing dose 1 against dose 2. So we'll select comparative study with 2 arms. Why 2 arms? Because there are only two groups in the study, dose 1 and dose 2. If we're comparing 3 doses, dose 1, dose 2, and dose 3, then we will come to comparative study with 3 or more arms. But for the sake of that illustration, we had this one. So the first thing we have to do is put the prevalence of the outcome among the control group. So the control group was the standard dose. If you remember that question, the question was, how does dose 1 compare, or this particular dose compare with the standard dose? So the standard dose is the standard of care or the current treatment that is being given to patients. So what we're asking here is, what percentage of patients who are on the standard of care report symptoms of anxiety? Let us say that percentage is 15%. We don't know what that is, but I'm just making it up. How do you know what that number is? Well, you go and do a literature review, and that's how you know. So we provided 15% there. Now we have to provide one of 4 values here to determine effect size. Effect size is
please, with that, are you? Hello, boss. So with the 15%, are you getting it from?
I'm having difficulty.
Articles, or is when you're already. Hello.
Will you please repeat yourself? Okay. Well.
Hello.
Yes. Go ahead.
Hello. Hello.
Yes, we can hear you. Go ahead.
I mean the 50.
Okay, you know what? Can you just type your question in the chat box? I think you're really struggling with your internet.
15%. Yeah, the 15%. Or you take it from the raw data. I mean the 15%. Where do you get it from? Is it from articles or from your raw data?
Okay, the 15%. It can't be from your raw data because you are trying to calculate sample size to do the study, so you don't have the data yet, okay. Right? So in this case, I'm saying you should go and do a literature review to see what other studies have done. What did other studies find out in terms of the percentage of patients on this treatment? How many of them have anxiety symptoms? So it can't be from your data because you don't have the data yet. You can go and do a literature review to find it. It doesn't have to be in your community. It can be, because we can argue that biological responses are likely to be the same across populations. So the way that a particular population will respond to it might be the same as another population. So that assumption can be made, but it's something you can get from the literature review. Now, if you cannot find that all in the literature review, well, you can convene a group of experts and ask them, well, what do you think, right? One of the things you have to realize is that sample size calculation is a scientific guess because we're just trying to get an estimate. So it's not, I think it's like 100% foolproof. So that any educated guess is better than nothing at all. It's better than just coming up with a random number from your head, right? So, but for the sake of this demo, I am just making up the numbers. So I just want to be clear, right? So for the sake of this demo, I'm just making up the numbers.
Thank you.
All right, great. Now you have to choose a quantity below and enter its hypothesized value to assess effect size. Remember that effect size is the difference we want to detect between drug 1 and drug 2, right? The smaller the difference we want to detect, the larger the sample size we will need. So remember we said that, a powerful microscope will be needed to detect small differences. So if we want to detect very small differences, that means that we need a much bigger study. And there are many ways you can express that difference you want to detect. You can express it as a prevalence ratio or as an odds ratio or absolute prevalence difference. But let's say that I hypothesize that this new drug is extremely good and that I think it's going to reduce the prevalence of anxiety among my patients. So I think that the prevalence will be, let's say, 10%. I think that on patients who are on this new treatment, the prevalence of anxiety symptoms will be 10%. So that's where I select that indicator and I enter my value. Next, I provide a level of confidence.
So in order to become a professional forex trader, you will need to know
Mr. Forex Trader, can you please mute yourself?
use these 3 types of forex
Daniel,
market.
Daniel Ogochukwu, please. Can you kindly mute yourself? We have zero interest in your Forex ventures. Thank you. So that level of confidence desired, I provide 95. Is the test one-sided or two-sided? You always want to go with a two-sided test, right? A two-sided test is like crossing the road. See, right from when we're young, we are told, look left, look right before you cross the road. Don't just make an assumption and look left and assume that there are no cars coming to kill you from the other direction, right? Now, a two-sided test will obviously take more in sample size, because think of it just from common sense. If you're looking both sides of a road, it takes you more resources. If you look to the left of the road and you look to the right of the road, that takes more time than it would have taken for you to have just looked at one side only. But the idea is that research means we don't know what we don't know. So we can't assume that the relationship will go one way. We have to acknowledge that it might go that direction or this direction, and that's why your tests have to be two-sided. The power desired, you should typically enter values between 80 and 90. Anything lower than that means that your study might not be powered adequately to detect differences. I provide a ratio of controls to cases as 1, since a ratio of 1 to 1, and the anticipated response rate I provided as 50, and I calculate the sample size. This tells me that I need 393 people in the treatment group and 393 people in the control group, or a total of 786 participants in my study. So I can show the reference here to get the formula that was used for the sample size, right? Now, very important things to note. 1, statistical power is driven by the smaller arm. So you always want to achieve some kind of statistical balance between the two arms. It doesn't help you if you have 786 people in your study, but you have 86 people in one arm and 700 in one arm. No. That study is not well powered, because remember that power is driven by the smaller arm. So 2 studies, both have 786 people. Study 1 is balanced, it's well powered. Study 2 has the exact same number of people, but it's not balanced. It has 700 people in one arm, 86. That is not a good study, right? So you want to strive for balance, because again, take-home lesson is that power is driven by the smaller arm. So now I can use this formula. If I'm writing the grant, I can download the formula. I can also copy that citation and also include it in my work, right? So that is how I could calculate sample size for a confirmatory study. Now, if the study is just exploratory, that is the same as calculating sample size for just a descriptive study. Sorry, your hand is up, Lion King. Okay, maybe that's an old hand. All right, so that's how you calculate sample size for a confirmatory study. So if you have questions, please, you can ask before we leave that.
Yes, Prof, my question here is, how do we know the author of the formula behind these calculations? And then is it possible that for academic purposes, whether the software can show step-by-step calculations before it arrives at the final answer, like 786?
Well, okay. The step-by-step calculation is what's in the formula. That's why you have a formula there, so that you can, if you want to do it manually, you can use step-by-step. And these are standard formulas. These are standard formulas in science. So regardless of the tool you're using, that's the same formula that we use. But the calculation has not been done. It's not been done by one guy sitting behind and writing it. It's been written by code. And that's why you have this formula there. So in case you want to say, oh, I just want to do it by hand, you can, because science has to be reproducible. Meaning that if I generate a particular result, you too should be able to use the same formula and get the same results. And that's why you have this provided for purpose of reproducibility. I hope that is clear. Any other questions?
Okay, sir.
Yes, sir.
Thank you for the lecture. You said something about the power is driven by smaller arm, and also you talked about that the connection, so that we can able to get the accuracy, it has to be small r. And furthermore, you also also mentioned that when you want to do with a kind of grant and the likes, these are the things that they pay attention to. So we appreciate if you can just expatiate on them, sir.
On which one exactly?
On how can we get the power out, because I'm kind of confused with the concept behind it.
How do you get the power what? The power up?
Yes, sir. The power. You said the power is driven by smaller r.
Oh, okay. Power is not a physical construct. Power simply means like it's the same way we say the power of a microscope. When you say microscope is powerful, you are simply saying that, wow, that microscope can detect things, that even the smallest things can detect it. So we mean, when we talk about power, we're not talking about power like in the concept of like, wow, you have a lot of muscles or anything. We're saying that your power simply means that you have a big study, right? And so that's what it means in the simple terms. And so you don't have to manually try and figure out what the power is, right? That's why you have tools like Chi-Square's platform that allow you to do that. Here in this calculation here, we have this power desired. Just know that a good power should be above 80, between 80 and 90%. That's what you should strive for. So you don't have to master a lot of things. Just know the basics. And if you look at the hints here, the platform also provides you with hints. So for example, let's look at the hint for power. It says that just like a powerful microscope allows us to detect small things, a powerful study allows us to detect small differences. Power is calculated as 1 minus the probability of a false negative and is expressed as a percentage. We recommend using the power of between 80% to 90%. So everything you need is already provided for you. So you can just read the hints and then just follow what is said. Now, if you now want to go and do something else, that of course you can, you're free to do that, but the recommendations are there for you to just follow and just use as suggested. I hope that clarifies.
Understood, sir.
All right, great. Any other questions?
A quick question from me. I was going to ask about the effect size, which is a bit different from the power. So how about if you are designing a case control study and then you have an anticipated, let's say, effect size, you want to detect at least, let's say, 15% differences between the cases versus the control. How do you fit in that into this equation? And then you also may want to say a case to a ratio of maybe case to control ratio of 1 to 3, 4, and the higher the much powerful the study would be. How do you account for that here?
Okay, so in the concept of a microscope, let's go back to an analogy. I like simple stuff. Again, an analogy, the effect size is the size of the small organism on the microscope. That is what the effect size is, all right? So the power is the lens. How powerful can the lens detect the small, tiny microbe that is on the microscope? So in the formula, we present the effect size as delta. Now, on the app, we provide you with a lot of ways to think about how do you want to capture the effect size. If I'm talking about a case control, let me go with the example you mentioned, the case control study. In the case control study, what we calculate is matched odds ratios. So it will make sense for me to use odds ratios. Please, can you kindly mute yourself if you're not interacting with the class? So if I'm what was I saying? Case control studies, yes. So in that case, I may want to have odds ratio as a measure of the effect size. And in that case, I might say, okay, I want to detect at least an odds ratio of 1.5 between the cases.
Good girl.
Nkomo Sikan Selva. Can you kindly mute yourself, please? All right. So we provide an effect size of 1.5. And here we say we want to have an, let's say, ratio of cases or controls to cases of 4, right? the scenario you pointed, and we click on get results. So that tells me that for my cases, I need 56 cases and 221 controls, right? In a case control study, having up to 4 controls per cases increases the power, but beyond that, it doesn't help you. So if you now have 5 controls to a case or 6 controls, it doesn't help you beyond 4, right? So that's why we typically cap, the ratio of controls to cases at 4 in the case control study. But yeah, so you can play with this regardless of the parameter you supply in here. They're all roads lead to Rome, as I say, right? Whatever parameter you supply here is now used to calculate the delta, which is then fed into the formula. But the many options here is just to give you variety and options, right? There are mathematical relationships between each of this. All these things have mathematical relationships between them. So regardless of whatever you supply, we use the mathematical formula that relates to convert the parameter to what we need eventually. So here you can use whatever parameter or option that best suits what you're trying to capture. I hope that makes sense to you.
Yeah, it does. Thank you so much.
You're welcome. Any other questions?
Yeah, Prof. So what about those of us who are doing quasi-experimental studies and we want to reduce, for instance, I want to reduce malaria burden from 51%, about 10% reduction. Is this which of the indicators should I use?
Okay.
Should I use the prevalence of outcome?
It doesn't matter. All of them, you can use any of them, it's fine. Any one of those would all roads lead to Rome, remember? Use the one that you are most comfortable. So it's all about your comfort. What do you have on hand? So we don't want a scenario where you got a result from another study as 1.5 and as odds ratios, and there is no allowance for odds ratios in the app. And you now have to start saying, how do I convert odds ratios of 1.5 to prevalence? That is unnecessary, complex and making the app user unfriendly. That is why you have all these options to calculate it. You can just fit in whatever you have on hand or whatever you're most comfortable with. I hope that makes sense.
Yes, please. Yes, please.
Okay, great. Any other questions?
Yeah, thank you very much, Professor Agaku. I just want to follow on from the question the last but one person asked about case control studies. And I wanted to ask if a study, having calculated your sample size, would you say a study that has a 1:4 cases to control would be more powerful than one that has maybe a 1:1 ratio?
Yes, and that's the whole reason why we do it, to increase the statistical power so that we can detect differences. But anything beyond that doesn't add any added advantages. Now, that arbitrariness in addition of cases or controls of cases is also the reason why we can never use case control studies to calculate prevalence for the population, because the denominator is arbitrarily changed, whether we selected 1 control or 2 controls per case or 3 controls per case. The denominator of the study will arbitrarily constantly change. And so with one selection, you might have a prevalence of 22. And so that is why we can never, ever use case control studies to generate population prevalence. But yes, the reason why we do that is to enhance the power of the study.
Okay, thank you. But would the case we just did, where you had, is it 700 and something, the sample size you needed was about 700 and something, and you had 1:1. Is it possible to calculate it and have a 1:2 or 1:3 just to increase the power of the study?
Yeah, in general, whenever you're doing sample size calculation, it's always it's not a very good idea to just have one single number and just show to the grantor and say, hey, this is sample size calculation. It's always better to have a grid, a table, where you show the differences in assumptions. Like, okay, in this case, let's say we're using a ratio of 2 to 1 or ratio of 1 to 1, or we're assuming power of 80% or a power of 90%, and so that the reviewer gets to see the whole range of possible, and the potential impact on the study. Because at the end of the day, the study's feasibility is driven not only by statistical considerations, but also logistical and frankly, money, right? So that's why you want to have a wide range of assumptions, so that you look at every possible scenario, so that should your resources take you to only so far, you can know that, well, it's not that bad. Given the other options we had, it's pretty close to the other assumptions. So so it's always a good practice to come up with a grid of table or a grid of calculations under varying assumptions.
Okay, thank you, much appreciated.
But definitely, you're welcome.
I was gonna.
Hi there, Prof. Okay, sorry. Go ahead.
Okay, I was going to ask if the same, let's say, assumption holds for cohort study as well, because last month I reviewed a paper where that was actually in Sweden, a nationwide cohort where the entire country is within the cohort study, and that particular study used a ratio of let's say 1 exposed to 10 unexposed group. The ratio of, if you want to coin it to case control, it's like a case 1 to 10. And then part of the methodological component of that, we argued that, in fact, with my professor, that it is a very powerful study. The fact that they could have 1 to 10, the higher the value for cohort study, the more power the sample would be, like the whole analysis would be. So my question is, could the same assumption be different with cohort, even though some professors are arguing that the higher the ratio variation, the much powerful your sample would be? I just want to know your opinion on that.
So ultimately, right, depends on the outcome. So if in the case of a cohort study, right, so epidemiologically, right, following 10 people for 1 year is the same as following 1 person for 10 years, right? Either way, we have 10 person years, right? So the question then becomes, what should we do? It depends. The answer is, it depends on how rare the outcome is. If the outcome is very rare, no matter, even if your study had 1 million people in the world, and you followed the 1 million people and not one outcome not one case of the outcome was detected, that means that your study is completely useless. We cannot calculate anything from the study, right? So we need to really, some of these things are more nuanced, because we then have to take into account the outcome. Like, how prevalent is the outcome? What's the rate of the outcome? And how many anticipated cases do we expect across the groups, right?
Yeah.
If I expect, go ahead.
Okay, so the study was actually 20 years period, and then the outcome was the main exposure here was body dysmorphic disorder, BDD, and then they were having 2 exposures, intentional self-harm and then suicidality. Those are the 2 outcomes they were measuring. So within the span of 20 years, they were able to have about, let's say by cases, it's not much. It's like 17 cases mortality within the suicide intent, and then about 27 in the other category. So it was basically a 20 years span period. And then those diagnosed of body dysmorphic disorder were the exposed, the non-exposed are the non-diagnosed, and they were matched by age, sex, and then address, more like county.
Okay. And so you can see that without reading much of a study, you can see already that one of the major considerations by the authors must have been also the issue of competing risks, right? There's a risk in your study you want to capture, but then competing risks are other things that take individuals and make them censored. Censorship epidemiologically means that the person disappears before we got to observe the outcome of interest. If the person, like suicidal ideation, if that is an exposure group, well, maybe that person will have killed themselves before we ever got a chance to really study the outcome of interest in that. So we've lost that person to competing risks. So the question is, how then do we ensure that we have enough of those people to actually capture the outcomes of interest, right? Those are some of the considerations that will then make you determine, oh, I want to have 10 of those ones to 1 of those, because those ones are more prone to be lost to competing risks, right? So some of these things aren't necessarily like black and white, and in general, right? I think there's things like this, there's an art form to them. It's both a science and an art. And so I generally wouldn't be too worried about, oh, is this more powerful or less powerful, as opposed to careful considerations of things like competing risks and ensuring that, you know, we have ability to capture these people over time, and that you know, we control attrition or loss to follow up. Because obviously in this case, it's quite clear that you will most likely have differential loss to follow up between the two groups. You most likely also have differential, differences in mortality, right? Not related to the outcome of interest between the two groups as well. And all of those things have to be considered, right? To make sure that at the end of the day, you have rates of the outcome in both groups that allow you to be able to capture, the differences you want to detect. So I think a careful consideration of those kind of matters is more important than at the end of the day saying, okay, that they more of a simplistic looking at, oh, this, I think it's more complicated, that especially with this kind of outcomes that are very prone to competing risks, then you have to really make sure that you have enough people that you can follow them for long enough periods to observe the outcomes of interest. So I think it's not black and white. It's a gray area that is such subject to a lot of considerations and nuance.
Yeah, thank you.
You're welcome. Any other
Hi
questions?
there, Prof. Hi there, Prof. Quick one, Prof. Prof, can you hear me?
Clearly, yes, I can hear you.
Yeah, I just wanted to find out. I've actually done 2 surveys on the chi-square platform, which I'm yet to launch, because I'm also yet to calculate the sample space. So what I'm doing is eventually going to use a structural equation modeling framework. And sometimes for that, you need, in addition to the statistical power, you need a number of latent variables, number of observed variables, and stuff like that. Are you able to customize the chi-square sample size calculator for specific studies like that?
So latent variables are not necessarily, the reason why we call them latent is because they are hidden, right? Latent variables are not observed. So you calculate you design your instruments. If, for example, I'm trying to measure, I don't know, what's your outcome?
How do you mean, sir?
Like,
oh, right. I mean, we're trying to see the effect of artificial intelligence mediating emotional intelligence in engineering management.
Okay. So the question then is like, what emotional intelligence is a very hard construct to measure, right? Because there are so many indicators that might feed into this construct called emotional intelligence, right? So the
there
whole
are
idea,
about 5 of them.
Okay, great. So I'm not an expert in that field, but so you could definitely look at several indicators that say, okay, what is emotional intelligence? How do we capture it? And then from those observed variables, you can then derive the latent variable. So that is more of a statistical construct. It's not necessarily a sample size consideration per se. It has more to do with the quality of the variables. So this is a bigger issue here is about measurement error, right? Measurement error in the terms of how am I capturing the variables? How am I designing the questionnaire, right? Like you said, there are 5 items to that construct, but are you sure?
Yes.
It could be more.
There are 5 of them that are broken down, that from which you can actually break out the questions, which become the observed variables.
Okay. So my point here is that in your case, right, the bigger issue here will be issues of measurement error and measurement bias as opposed to sample size. So your sample size calculation will still follow the standard calculations, but then you would really want to pay attention very carefully to issues of measurement bias, especially in those constructs, and ensuring that you really are following standardized constructs so that your study is comparable with others.
Oh, okay, that's fine. That's fine. All right, thank you for now.
You're welcome. Yeah. Okay. Any other questions?
I was going to take you back to the bias section where you mentioned the measurement bias or something. So could that be grouped within the bigger picture of information bias, wherein we have that misclassification, differential and non differential, and all of that embedded within?
Yeah.
I've seen a couple of textbooks that categorize measurement within information bias. And then at the extreme arm of confounding bias, we have that colloidal stuff, where there are unconditional blocking stuff. So I don't know whether those causal pathway explorations may be something you'll be covering in this course.
Yeah, we've taught courses on causal inferences, and we can have another course if that's but my experience is that when we teach such advanced stuff, I find it, I feel that the audience is very uncomfortable, but we can definitely have that session. We can definitely have another more methodological sessions that are more in-depth and look at some of the more complex issues in epi. So yeah, but definitely that's something we could have. But yeah, going back to your original point, different people call things differently. And that's why for me, generally, I always encourage.
Listen, can we just finish?
Sorry? That's why in general, right, I'll generally recommend more of understanding the fundamentals as opposed to semantics or whatever it's called. That is generally less important than really understanding at the heart of it what the issue is, right? And how we address it. So, whether we call it information bias or measurement bias, that could be subject to discipline or different experts with different opinions. But essentially, we're still saying the same thing. So yeah, I definitely agree with you that there's quite a lot of variability in how things are called. But at the end of the day, measurement bias has to do with how do we measure and what are sources of error. And those kind of errors could be, we can classify them in different ways, right? We can classify measurement bias as measurement from sampling sources or non-sampling sources, where non-sampling sources could be like, how we construct our measurements. Because the unique thing about human research is that as you are studying the participant is also studying you. So it's, in a nutshell, what are the biases that come from me studying you? And what are the biases that come from you studying me as the investigator? In a nutshell, that's what we're saying, right? Me studying you has to do with how to construct my questionnaire, whether it's leading, whether it's biased, whether it's double-barreled, and so on and so forth. You studying me has to do with social desirability bias and all the other things that have to do with social judgment and cognitive heuristics. And so as long as we understand at a fundamental level, yeah, whatever we call it is really material. So, but yeah, we are definitely going to have sessions on causal inferences and colliders and all of that for people who are interested in those kind of more advanced topics. Any other questions?
Prof, please, can we go on?
Yeah.
No, I think that we can look at more details about this. Prof, do this formula take consideration of can this formula take consideration of attrition rate?
Yeah, the attrition rate.
Prospect.
Yeah. Sorry, I interrupted you. Please go ahead.
Oh, for cohort studies.
You don't? Oh, yeah. So yeah, it does. That's why we have that transient response rate.
You can take a question. Like which one is some question wants to put you? Even then, you can answer very question. So you're taking us back. What's the party? What's the tire the question?
Can we have some measure of? We can sing together, but we can't talk together. So please, can you mute yourself? Thank you. Lungi, can you please mute everyone? Okay. I have completely lost my thoughts. Sorry, what was the question again? Oh, your attrition rates. Yes.
Yes, please.
Yes. The platform takes adjust for attrition rates, and so the opposite of attrition is response. So they are complements. So well, I'm completely disoriented now. Alrighty. But So the attrition rate and response rate are complements of each other. The opposite of response is if I responded, that means I did not fail to respond, right? Or if I suffered from attrition, that means I did not respond. So you provide the response rate, which is the opposite of attrition. So yes, it accounts for it. In a nutshell, that's the answer. Does that make sense to you? Okay, take silence as consent. So, any other questions? So we have actually come to the end of the session today. Today's session was just to provide us with a high-level overview of what the key topics we need to know. So again, these are the topics, these are the key elements we covered in terms of establishing a common knowledge base. We've talked about hypothesis testing, p-values, univariate, bivariate, multivariate, and multivariable analysis. We've talked about issues of bias and validity, and then power and sample size requirements. So next week, we will build on those things and we'll dive into the first regression on our list, which is binary logistic regression. So please read ahead of the class and read all materials you can find on binary logistic regression, so that when we have a session next week, you have questions to ask and any concerns that you experience to be answered. All right, that's all from me, unless there are other questions I need to answer.
Sir, please, you were showing us an example on how you could use the confirmatory on, but you wanted to make an example of exploratory on. That's when the questions kept coming in. I don't know whether you could.
Oh, I see. Yeah, okay, all right, let's do that. Alrighty. All right, so for exploratory, right? So remember that there are two P's, precision, power, two very different things. Precision has to do with how wide or how narrow are our confidence intervals, right? When we're doing exploratory analysis, that's what we care about, worry about. Whereas in confirmatory analysis, we worry about power. So please know the difference. Those two are not the same thing. Precision and power, very different things. Precision and validity, very different things. Validity means the truth. You can have a result that is very precise, but completely wrong. Precision simply means you have very tight confidence intervals. That's what a precise result means. So imagine you have a result from a very large convenience sample. You have 1 million people who participated in that convenience sample. Of course, you're going to have very tight confidence intervals, but that doesn't mean that the results have external validity, because they are from a non-probability-based sample. So I just wanted us to establish the difference between validity and precision, and between precision and power. Power only applies when you have a comparative and an analytical study. So if you have a cross-sectional study, this is a common mistake you see. People talking about power in the context of a survey. Like, that doesn't even make sense, right? Like, power only exists in the context of an analytical study where you're trying to compare two or more groups. So just to make sure we are not making any assumptions about knowledge. So in that kind of case, again, you just have one large sample. There are no two groups being compared. And exploratory analysis is part of descriptive analysis. So the same way you will address calculating sample size for your survey overall is how you will also address calculating sample size for your exploratory analysis, but you will just make sure you pay attention to the margin of error. So that's where you want to pay attention. If you're also going to do subgroup analysis, you might want to pay attention to that carefully. But in this case, let's go ahead and just do a quick run through. And just to add, for those of you who might end up working in CROs, contract research organizations, we actually don't do sample size calculations for exploratory analysis. Why? Because the data we get, it is what it is. Because let's say I want to do a study of patients who are on this new drug, let's say dolutegravir, and there are patients who are from multiple centers. I am getting all the data I can get from them, right? It's not, so all the data I get is what I get. It is what it is. I don't have the luxury of calculating sample size. So just to expose you a bit to the commercial aspect of scientific research, that we typically don't calculate sample size in those kind of contexts where we're just getting all the data we can, because it's exploratory analysis anyway, right? So in that case, what we just worry about is the precision of the estimates, like how wide are the confidence intervals. And so that's, again, something that I think it's important to mention. So in this case, let's say that I want to calculate the sample size for a survey, and I want to use that survey to do, just explore factors associated with smoking. So sample size calculation for the survey will be the same as the sample size calculation for the exploratory analysis, but with particular attention to a few parameters here. So here, for example, I say the outcome is categorical. I provide a level of confidence as 95. The prevalence of the outcome is 50. And 50, again, is where we get the maximum variance. That's why we use 50, in case you're wondering what's so special about 50. If we say that the country is highly polarized, it means that 50% of the population support this president and 50% support the other guy. That is the maximum polarity you can get when the country is evenly split in two opposite directions. So that should help you realize that variance is maximized at the prevalence of 50. All right, that's why we say if you don't know what the prevalence is, just go ahead and use 50%, because what that happens is that guarantees you the maximum sample size possible. So it's like aim for the moon. If you miss, you hit the birds. So we aim for the maximum sample size if we don't know what the prevalence is, so that we know we are covered regardless of what happens. That is the idea behind using 50%. Next, we provide the population size. The population size doesn't really matter. So some people really get into get themselves into a frenzy about, oh my gosh, what's the size of my population? Like, I need to know that it's this exact number. It doesn't really matter, especially when the population is big. If your population is 100,000 or more, you don't even have to worry. Just put any number above that. It's because sample size is agnostic of population size. What does that mean? It means that the sample size I need to calculate the prevalence of smoking in the city of Boston is the same I will need for the state of Massachusetts or for the entire US, right? Because it doesn't matter. I will demonstrate that in a second. So it only matters when the sample size, when the population is small. So if I have a very small population, let's say I'm trying to look at prevalence of smoking among, let's say, doctors in a local government area or doctors in the county. Well, in that case, that is not a really large population, right? Then the population matters then. And the reason why it matters is because of a mathematical construct which we call the finite population correction. The finite population correction, or FPC, simply is based on the premise that the sample we have is a very, very, very small proportion of the larger population. So we say the sample is infinitesimally smaller than the parent population. But the question is, what if it is not? What if the sample is actually a huge chunk of a parent population? Well, that means that that assumption is violated. That is the only time we need to worry about the population size. Because if you look at the formula for, which I'm going to show you in a second, population size does not even appear in the formula for the sample size calculation for a survey. But we need it to just adjust for the FPC, which is the finite population correction factor. And then you indicate whether cluster sampling will be performed or not. And this is very important in the context of regression analysis, even if you don't realize it. When we use cluster sampling, that increases the width of our confidence intervals in general, right? So cluster sampling in general, when it's associated with wider confidence intervals, because there's just greater variability in the outcomes, right? There's and so that would definitely lead to much wider confidence in your results. But let's say we're just doing a simple random sample. We provide a margin of error as 5. The margin of error is the half of the width of our confidence interval. So the confidence interval divided by 2, and that's what the margin of error is. So that implies that if you want confidence intervals that are very tight, you're going to have a smaller margin of error. But if you don't have enough money, if I'm doing a budget, if I'm doing a grant, or applying for a grant, and I see that, okay, the cost, because I have to account for the cost of recruiting the patient, I have to account for the cost of incentivizing the patient. Maybe I'm giving each patient $20, right? And so many other costs that are unit costs per patient. Obviously, the budget for the grant is fixed. Then I may now start looking for ways to reduce my sample size so that it falls within a reasonable limit, right? That's when I can now say, okay, all right, with a margin of error of 5, geez, this sample size is quite high. This is way beyond my budget. How about I take a compromise here and just accept wider confidence intervals by increasing the margin of error from 5 to 7 so that my sample size now drops. It's now 392. Okay, now I can afford this, right? So you provide a justification, and so that's how you do it, right? And so this would be how you would calculate the sample size for that kind of context where you're just doing exploratory analysis. It is the same as for a descriptive analysis, which is in this case, survey. Like before, the references here show you the formula that was used, which you can download. It also explains what each of those parameters mean in the formula. Any questions on that? See.
Hello, thank you very much, sir.
You're welcome.
Okay. From the explanation you made mention, you talked about the exploratory analysis, whereby we need to consider the sample size. Well, you said it is peculiar to survey. So one of the things I noticed is that from the discussion, from what you display, I was seeing something called cross-sectional analysis. So is there, because I believe that cross-sectional analysis is kind of a survey that is done over a period of time. So does this also affect this concept about exploratory analysis?
Yeah, exploratory analysis is not only limited to surveys. Just to be clear, you could have exploratory analysis even within a clinical trial where, for example, a researcher wants to, let me pull this paper to show you. I think this will answer your question. But before I do that, right, imagine you have a clinical trial and you took clinical trial data and you're now looking at just a whole bunch of subgroup analysis that were not originally accounted for in the original trial. That is also exploratory analysis, right? Let me pull up a study and just demonstrate what I'm trying to do. So it is not necessarily restricted to all right, let's see this. So here, what we did was we took so as the very first word, as you can see here, is exploratory analysis of clinical trial data. This is clinical trials, but it's so that alone should tell you that you can have exploratory analysis even within the context of clinical trials. So what we're trying to answer here is, what are the dangers that come from when you do excessive, how will I call it now? When you excessively beat the data, for lack of a better word, right? And so the reason for this study was because the health technology as HTA agencies generally would require. So there are two agencies in many countries that are related to the regulation and approval of medications. You have the regulatory agencies like the FDA or the European Medicines Agency that would review the results of the clinical trial and approve that, yes, this drug is efficacious and safe. Those are the two things we look out for in clinical trials. Is it efficacious and is it safe? Now, you have HTA agencies, which are now like responsible for now approving the medication to be used among patients and paying for the coverage and all of that. HTA agencies would generally sometimes require that a lot of, after the clinical trial has been done, that would take the clinical trial data and would do a whole bunch of analysis, right? And sometimes it could run into hundreds or thousands of analysis of small subgroups. So in this case, we're saying that there is a lot of danger in that. So if you look at this table, for example, this is showing you just some of the, in some of the exploratory analysis, right? You have as small as 6.9% of the analysis of this original sample size was used. So imagine this, the original sample size was calculated as 100 people that was needed. And here you come and say, oh, we have 6.9 or 7 people we're going to use for this subgroup analysis. Well, that's very dangerous. Why? Because you are almost guaranteed to have type 2 error, which is that you are unable to detect differences. Not that the differences don't exist, but because the sample size is way too small. So the bottom line of what I'm trying to say is that exploratory analysis is not a feature that is restricted to surveys. You can have exploratory analysis of anything. I hope that is clear.
Yes, sir. Thank you very much, sir.
You're welcome, yeah. Any other questions?
Yeah, hello, sir. I have a question.
Yes.
Okay, my question is regarding like maybe I have a time series data. Is that one, must I calculate the sample size too, or I can just use as much as possible data sample that I can get?
So what do you mean by time series data? Because some of these terms are used by people with very, very widely varying meaning. So I need to understand what exactly you mean by when you mean time series.
Okay. Okay. For instance, let's say I'm trying to look into the trend of unemployment rate in Nigeria, and I got a data set from like maybe 2000 to 2000, like a monthly data set, like they recorded it on a monthly basis from maybe 2000 to 2024, something like that. Do I still have to consider maybe probably I'm using too much data set or lesser data sample? Do I have to be afraid of maybe it will affect my result or not in that kind of scenario?
Okay, so in that case, what you have are so that in general, when you talk about time varying data collections, there are two major buckets we have. We have repeated surveys, right? And then we have longitudinal surveys. Those are very different. They sound similar, but they're very different. In repeated surveys, which sounds like what you're describing.
Hello,
Can you kindly mute yourselves, please?
Yeah, just reach airport. I mean, don't forget to send me that stuff to my OPM. All right, thank you.
I don't know what we can do in the future to have an interactive session, yet one that is not disruptive, but we'll have to figure it out. See, I've lost my train of thought. Oh yeah, we're talking about.
You are talking about longitudinal.
Yeah, longitudinal and repeated. So what you're describing sounds to be a repeated survey. Repeated surveys is like in Nigeria, I come this month, I take a sample of a country, I come the next period, I take another sample. Now, there may or may not be some people that were captured the first time that may also be included in the second time. But the samples themselves are independent of each other. The next time I come, I take another repeated sample that way, right? That is just standard surveillance, really. And that is how that is what we use to calculate trends over time. Each of those repeated data collections are assumed to be independent. And so the sample size calculation for each wave or each unique iteration of data collection will be the way you will calculate for any standard survey. All right. And then we can then calculate the sample size like that. Now, sometimes you want to calculate sample size and you want to make sure that you have enough estimates for some subgroup, right? So let's say you are very interested in a particular minority group that is, let's say, 30% of the population or 20% or 10% of the population. Well, that means that you have to increase your sample size by that factor. So you're going to take the sample size you calculated for the whole nation and divide it by 0.1. That is obviously going to increase the sample size tremendously. So there are huge implications when people, clients or governments say, oh, by the way, when you're calculating the sample size, we really want to make sure we have enough sample for this group. Well, in that case, this is when you need to know the subject matter very well, because then you have to contemplate, what are my options in that case? The options are that I could stratify the sample so that I make sure that that group is captured as a separate strata, right? And then I might sample disproportionately from that sample. I might oversample that group to make sure that they have enough representation. Or there are millions and one ways you can think, but this is why you need to know the subject matter to a very deep extent, so that you can on the fly implement adaptive sampling or adaptive measures to correct or to address concerns that key stakeholders have. But to cut a long story short, yes, you can use that sample, you can look at trends, there's nothing wrong with that. Just make sure that the sample size calculation for each wave is adequately powered, and so that you can have enough, you have enough samples for precise estimates.
Oh, okay. I think you actually did not get what I was trying to explain.
Okay, please, can you repeat them?
Yes, what I was trying to say is, okay, I already have maybe a data set with that has monthly, like, okay, it has months like January, February. Let's say January it's 01-2000, like I have 01-2000 observations like that, like January 2000, February 2000, like that's my observation. And I have another column that has unemployment rate, like each month. Do you get it now?
Oh, I see your point. Oh, okay,
Yes.
I see your point. What you should do is a joint point analysis, because the unit of analysis is a population level, it's not individual level. Obviously, you cannot among an individual. So you should look into using joint point analysis for that. Now, how many indicators are you looking at? Is it just unemployment, or you have a whole bunch of other indicators you're looking at?
Other indicators, not univariate, like other.
Yeah, I understand. Like, how many of them do you have?
Like let's say 5.
Okay, that's fine. But if you were to have a lot of estimates, a lot of parameters, like imagine you had like 100 indicators you were going to look at trends over time. You had unemployment, you have, suicidal ideation, and 100 of them. That's a lot. That's what we call type 1 error, just waiting to happen. So in that case, some practical, common sense things you can do will be to change the confidence level from 95 level of confidence to 99%. So that your estimate is measured at 99% confidence intervals, right? To account for the fact that you are doing way too many comparisons. You are looking at data too much, right? But yes, you can definitely go ahead and use your data. And so look into joint point regression. That would be a nice way to analyze that particular data you have. Joint point regression is a very easy technique, and you can definitely explore that with your particular question. I answered your question.
Yes, thank you so much, sir.
Okay, great. Any other questions? So, alrighty. If there are no other questions, we will call it a day then.
Yeah, thank you so much.
Thank
you for the training, for the meeting.
Any other thoughts, please?
No thoughts. Thank you so much, everyone. Let's meet again next week, and please share the link, the invitation. Invite those in your circle so they can learn with us.
Please, let's practice more. Let's practice better tech hygiene next time, please. If you're not speaking, just kindly mute yourself, please. That's for next time, please.
Very good, sir.
Prof, I was just going to say whether